Imagine that you are an eco-conscious cruise passenger from the future. You step on board your ship, and next to the ABB logo, you see that it says, "This is the world's first zero-emissions cruise ship powered by hydrogen." You start to ask yourself, what does this mean, and how is this possible? Well, we are H1 Technologies, and we want to show you how this is possible. We have developed the most feasible solution to solve the maritime industry's push towards sustainability by developing a blueprint for a hydrogen-based vessel with zero emissions throughout the supply chain. What we found is that through a HTPEM fuel cell-based system running off of a liquid hydrogen storage and a space-grade bunkering system, we can power a 3,000 pax vessel for up to 14 days. So now let's walk through it, starting with NIKOLAI and bunkering.
As to the bunkering system, it operates in two modes, filling and thermostating. In filling mode, the jet pump pumps liquid hydrogen at the temperature 21 kelvins from the on-ground tanks to the jet liquid cooler, where it's cooled down to 17-18 kelvins, from where it gets to the onboard tanks. In thermostating mode, to keep the hydrogen temperature within limits, the hydrogen circulates through the jet liquid cooler and the onboard tanks. There are two possible issues related to this system. First, since the ship is moving during the bunkering process, robotic arms should be used to compensate the ship's movements to keep the system sealed. Second issue, to thermostat the hydrogen on board, the pump, cooler, and all the necessary equipment should be placed on board of the ship, which can be difficult to do because of the equipment's huge sizes. So on-board thermostating is still an open question for engineers. The on-ground part of the system can be also placed on board of a special bunkering vessel. This will allow to bunker the hydrogen ship during the cruise or in case of emergency.
As for the storage, we have decided to combine two different technologies. A technology from Russian company called CryoMount and one from American Department of Energy. What you can see here is basically a CryoMount tank, but with metal materials replaced with high-density polymer liner and carbon fiber to make it lighter and more sustainable. The ship will have 10 tanks 11 meters in diameter each. Here you can see the amount of fuel needed for 14 days of voyage. Tanks also can be modular and replaceable throughout the voyage, which can ease the bunkering process.
And now, let's take a look at the method we chose to make energy on board: fuel cells. Through our comparison with multiple different kinds of fuel cells, we found that HTPEM fuel cells are the optimal powertrain for this vessel. That's because of high efficiency, low noise, and no emissions. But even though this kind of fuel cell is very promising, the technology is not quite there right now to power a vessel of this size. We propose creating larger individual fuel cells by increasing the diameter of the fuel lines and increasing the area of the catalyst walls, proton exchange membranes, and diffusion layers. This would then give us larger fuel cells, which we would stack vertically in pairs of 5, which gives us 2 megawatt output per fuel cell or 10 megawatt output per stack. We would then of course need 46 of these stacks to be able to operate the ship.
Regarding the power system, the propulsion system will be electric system, which means that there will be 2 electric motors on port and starboard side of the vessel. The output power of the fuel cell is DC power, and power converters are necessary to be installed to achieve a stiff applicable DC power source. Moreover, in order to meet the total power demand for the 3,000 passenger cruise vessel, it will be hybridized with the battery bank as the role of the energy storage system. So this figure shows the power system integration of the fuel cells with parallel electrical storage system. Apart from the propulsion system, separate fuel cell stacks for auxiliary power systems such as lighting, heating, instrumentation, etc. and also for emergency system will be arranged. Now, Nikita will continue with safety.
By their nature, all fuels have some degree of danger associated with them, but with hydrogen a number of properties make it safer to handle and use than the fuels commonly used today. For example, hydrogen is non-toxic, hydrogen is much lighter than air, and hydrogen is nearly invisible gas. Some of hydrogen's properties require additional engineering controls to ensure its safe use. Specifically, hydrogen has a wide range of flammable concentrations in air and lower ignition energy than gasoline or natural gas. Consequently, adequate ventilation and leak detection are important elements in the design of safe hydrogen systems. In addition, some metals can become brittle when exposed to hydrogen, so selecting appropriate materials is important to design of safe hydrogen systems. And KAUNG will continue with safety.
3,000 passenger cruise hydrogen fuel cell driven vessel, safety is also one of the most important issues. Therefore, not only do the vessel must comply with the IMO safety regulations, it will also follow the IGF code of the class rule, which is called the International Code of Safety for ships using gases or other low flashpoint fuels. Therefore, a risk assessment of fuel systems and design of the vessel must be conducted to meet the requirements of the code, which means that it will have an equivalent level of integrity in terms of safety and reliability with a new and comparable conventional oil-fueled machinery. So now Daniel will continue with the financials.
Here we see the cost of grey hydrogen or hydrogen created by non-renewable energy and the cost of green hydrogen or hydrogen created with renewable energy. Of course, in order to have zero emissions, we would have to go for the green option, which is slightly more expensive but not by a large margin. We've also found out that the estimated cost savings of such a vessel with no emissions could be quite substantial, especially if more countries start to adopt fair wage use, and the cost of emissions tax increase. Finally, we can see that the ship of this size can generate significant revenue per voyage as the consumer behaviors change towards more sustainable options, and this makes the project even much more desirable. Thank you.
So now, let us visualize what our system would look like using these 3D models that our team designed to help demonstrate what a system like this would really need on board. Here we can see the storage tanks, fuel cell stacks, and power system all working together harmoniously to power the world's first zero-emissions 3,000 pax vessel. So thank you for listening, and we hope this demonstrates to you that zero-emissions vessels are a real possibility of the future of large vessels. Thank you.